My name is Sima Frank, your mathematics tutor. Now, in this package, we are going to look at ordinary differential equation, popularly known as ODE. Before we start, let's look at the formats of the teaching. The course is mathematics. The topic is ordinary differential equation, ODE. Behavioral objectives. At the end of this teaching, the students should be able to recognize the order and degree of any differential equation. The students should be able to solve first order differential equation using direct integration method, using separation of variable method. If the first order linear equation is homogeneous, the student will know how to use substitution to get the solution of the first order differential equation. The students at the end of this teaching will also know how to solve exact equation. The student will also know how to solve second order homogeneous and non-homogeneous differential equation using undetermined coefficient method, operation D method, Laplace transform method. These are the objectives. Let's take the definition of differential equation. A differential equation is any equation of the forms dy dx plus ax y is equal b of x, that is 1. Can also be in this form: xy plus y squared dx minus x squared dy is equal 0. It's also a differential equation. Can be of this form: d square y all over the x squared plus a subscript o dy dx plus a subscript 1 y is equal 0. Can also be of this form: d square y all over the x squared plus a subscript o dy dx plus a subscript 1 y is equal f of x over 5. Can be of this form: partial square z all over partial x squared plus partial square z all over partial y squared equals 0. Okay. Can also be of this form: d cube y all over the x cube plus a subscript o d square y all over the x square plus a subscript 1 dy dx plus, okay, let's leave power for here, plus a subscript 2 y is equal f of x. Okay, so any of these equations, we say that a differential equation is any equation of the forms. So any of these forms. Now we are going to name this differential equation one after the other. Differential equation number 1 is called first order linear non-homogeneous equation. First order linear non-homogeneous equation. Now, differential equation number 2 is first order linear homogeneous equation. Now, for number 3, we have second order linear homogeneous equation. Differential equation number 4 is called second order linear non-homogeneous equation. Then we have differential equation number 5, which is second order partial. See, this is partial. Second order partial differential equation. Now we have differential equation number 6. This is third order. You see, I deliberately remove that place so that it will not be confusing. Now this is third order differential equation of degree 2. Okay, you see, the naming of these differential equations will soon be made known as we go further. Now, what we want to do now is what we call the order. We want to know the order, how to name order of differential equations. So that takes us to another subtopic where we have order of a differential equation. The order of any differential equation is the highest differential coefficients involved in the differential equation. All right. So we say the order of any differential equation is the highest differential coefficients involved in the differential equation. Now, it is assumed that the students are very familiar with elementary calculus, and that we should know what we call differential coefficients. All right, so differential coefficients is something like this. We have dy dx. So even d square y all over the x square, even d cube y all over the x cube, all these are differential coefficients. Now what we are saying here is that the order of any differential equation is the highest differential coefficient involved in the differential equation. So let's look at the differential equations that we have listed. And so that is why we call this first order, because this is first order differential coefficients. So differential equation will be named first order linear non-homogeneous equation. Non-homogeneous because here it's not equated to 0. It's not equated to 0. So this is a function. This is a function. B is a function of x. So if a differential equation is not equated to 0, then it is non-homogeneous. Alright. Now, this is first order. Of course, we know that if we divide this thing through by the x, we have divided x here. So suppose we transfer this to the other side, so we have x squared divided x is equal xy plus y squared. So this is first order differential equation. Differential equation, that is a homogeneous differential equation. It is equated to 0. Alright, now we look at the third one. This is second order. You see, we call it second order because the highest coefficients involved in this equation is g square y all over the x squared. That is the second derivative. So we call it second order differential equation. Now let's look at this. This is a second order also. Second order because the highest differential coefficients is d square y all over the x squared, which is the second derivative. So we call it second order non-homogeneous equation because it's not equated to 0 with constant coefficients, of course. S of the O, S of the 1, they are constants. And that is how this one becomes second order linear homogeneous equation with constant coefficients. Now look at this. This one is partial. I've said it, partial differential equation. You see, for students who are familiar with partial derivatives, they know that this is how we denote partial derivative. So when a differential equation involves partial differential equation, we call it a partial differential equation. So this is of order 2. Now we look at this one. It is of order 3 because the highest differential coefficient is d cube y all over the x cube, which is the third derivative. So we call it third order differential equation. Of course, it is non-homogeneous. You can see there is a function here to the right. Okay. Now let's look at what we call degree of a differential equation. Degree of a differential equation. Now, the degree of any differential equation is the highest power involved in the highest differential coefficients. Now look at that. We need to pay attention here because a lot of students are confused between what we call order and degree, but it's very simple. Now look at this. This equation is first order because the highest differential coefficient is divided x. Then we call it first order linear because in this place, of course, if I put this thing here, we should know that there is power 1 here. So when we are defining the degree, we say that the degree of any differential equation is the highest power involved in the highest differential coefficients. So even though there is another power that is higher than what is in the differential coefficients, that is not the degree. It is only what is in the differential coefficients. What the highest differential coefficient is raised to is the degree of any differential equation. Okay, so and that is why this equation, look at this equation, number 6, differential equation number 6. It is third order non-homogeneous differential equation of degree 2. Look at that, of degree 2, but look at this place. That was why there was something I wanted to put here, but I said let me remove it so that we can really see the picture very well. Now see, this is third order non-homogeneous differential equation of degree 2, not degree 3, because this 3 here is involved in a differential equation, a differential coefficient that is smaller than this one. Is it? So this one is the highest differential coefficient and it carry power 2. So we will name this equation based on that power. And so we call it third order non-homogeneous differential equation of degree 2 because of the degree that is involved in the highest differential coefficients. So that is how the degree and the order of a differential equation is mentioned. All right. So now let's look at another subtopic, and which is a formation of differential equation. We look at formation of differential equation. A differential equation could be formed from any given function by differentiating the function if a function contains an n arbitrary constants, then the function must be differentiated n times so as to remove the constant. It follows that a function which contains n arbitrary constants will give a differential equation of order n. So what we are trying to say is that a differential equation can be formed from any given function by differentiating the function. So if we are given a function, we can differentiate the function to form a differential equation. If a function contains an n arbitrary constant, then the function must be differentiated n times so as to remove the constants. You see, when we are given functions and the function contains maybe two constants, we must differentiate the function 2 times so that we can remove the constants. If it contains 3 arbitrary constants, then we differentiate it 3 times. So it follows that if a function which contains n arbitrary constant will give a differential equation of order n. The reason is that we are going to differentiate it based on the constants. If it is 2, we differentiate it 2 times in order to remove those constants. So in that way, we form a differential equation of order 2. If it is 3, so we expect a differential equation of order 3. Now, let's look at example. Let's pick example. Form a differential equation on the function y is equal a exponential 3x plus b exponential 2x minus c exponential minus x. Now, we see that this function contains 3 arbitrary constants, that is a, b, and c. And so we expect a differential equation of order 3. Now let's take the solution and see how we can form a differential equation from this given function. The function is y is equal a exponential 3x plus b exponential 2x minus c exponential minus x. Call this equation 1. Now, if we differentiate it, we have y prime. Y prime is the same with divided x. We know that very well. So y prime will be 3a exponential 3x plus 2b exponential 2x plus c exponential minus x. So this is equation 2. That is the first differentiation. So we'll differentiate it again. We'll have y prime prime will be 9a exponential 3x plus 4b exponential 2x plus minus c exponential minus x. So we have equation 3. So we have differentiated first and second. We are going to differentiate it again. Y prime prime prime, that is the third time, will be 27a exponential 3x plus 8b exponential 2x plus c exponential minus x. So we have these equations, and for us to form this, we are going to remove the constants, and we know that if we say 1 plus 2, that is equation 1 plus 2 will give us, or even though we say equation 2 plus 1, still the same. Let me put it that way so the arrangement will be proper. Equation 2 plus 1 will have y prime plus y, that is this 1 plus this, is equal 4a exponential 3x as this plus this, plus 3b exponential 2x, this plus this, and then this will go. So we have equation 5. Now, if we say again, equation 3 plus 2, we will have, for equation 3 plus 2, equation 3, this one, plus 2, we'll have y prime prime plus y prime will be equal 12a exponential 3x plus 6b exponential 2x. So we call this one equation 6. in doing that, when we add, this one will also go. Now, we still have another one here. I also see 4, that is equation 4, plus equation 3. And that will give us y prime plus y prime will be equal equation 4, this plus this, will equal 36a exponential 3x plus, we add this, we have 12b exponential 2x. So we have equation 7. So you see that we have succeeded in removing C. We want to remove B. So for us to remove B, we now see 6 minus 2 times 5. The reason is in 6 we have 6 here and we have 3 here. So by the time we times it by 2, the coefficients will be equal, so that we can remove it. Now that will give us y prime plus y prime minus 2, this is 5. So we say minus 2 y prime plus y will be equal this is 12 minus 2 times 4, which is 8. So we have 4 a exponential 3x, and this become equation 8. So we see that we have succeeded in removing b in that one, but we still have again to remove b in this equation 7. And for us to do that, we see that equation 7 minus 2 times equation 6 will make this, to become 12 like this. So we now see y prime plus y prime, that is this, minus 2 y prime plus y prime, will equal this is 36a exponential 3x minus 2 times this, that is minus 12. That is 36 minus, 24. 36, we have 36 minus 24, and that will give us 12. So we have 12a exponential 3x. When 2 times here minus 2 times here, it will be 12. So that goes that way. We have 9. We found out that in this place, if we can multiply this by 3, then the whole problem will be solved. So equation 9 minus 3 times equation 8, equation 9. So we give us y prime plus y prime minus 2 y prime plus y prime, minus 3 of this, that's minus 3, right? Y prime plus y prime minus 2 y prime plus y will be equal 0. That is because 3 times this, minus 3 times this will give minus 12. So everything becomes 0. So that to open up here, we now have y prime 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 plus y prime prime minus 2y prime prime minus 2y prime. Then we can open up here to have minus 3y prime prime plus y prime minus 2y prime minus 2y is equal to 0. Then we have y prime 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 plus y prime prime minus 2y prime prime 2y prime minus 3y prime prime minus 3y prime plus 6y prime plus 6y. Okay, this is plus 6y plus 6y equals 0. Now, this one is the third order y prime prime. So we have second order. We also have second order. And so what we have here is minus y prime prime minus 3y prime prime, which is minus 5y prime prime plus 1. So we have minus 4y prime prime. Now, we now go for first order. First order here we have minus 2y prime minus 3y prime. So that is minus 5y prime plus 6y prime will give us plus y prime plus 6y equal 0, which we can then write as d cube y all over the x cube plus, minus 4 d square y all over x square plus dy dx plus 6y is equal to 0. So in that way, we are able to form the third order differential equation. So that is how we can form a differential equation by differentiating and removing the constants. Now let's look at example 2 of how to form a differential equation. Form a differential equation from the function y squared is equal to 4a times x plus a. Let's pick the solution. Y squared is equal to 4a times x plus a. That implies that y squared is equal to 4ax plus 4a squared. Now, how many constants do we have? You see that we have one constant, a. Of course, a and a squared, they are still the same constant. So one constant. And so we expect a differential equation of first order. Now, let's call this equation 1. And if we differentiate, here we have 2y dy dx. Then if we differentiate, here we have 4a. Of course, by implicit differentiation, we know that this is what we have. Now making a the subject, of the formula, we have that a is equal to y divided x all over 4, which is y all over 2 divided x. So that is, this cancel this. We have that. Now, what we'll do is we are going to substitute. a is equal y all over 2 divide the x in 1, which is the original equation. And we do that, we'll have that y squared is equal 4a, and then we know that a is y over 2 divide the x times x, as this x, plus 4a squared, that is y over 2 divide the x squared. Now, what this gives us is, this will give us 2xy divide the x, that is because this can cancel this. And if we use x the times, we have 2xy. And this can also cancel this. But you must know that here we raise this to this, and this will also have the power. So we have 2. Of course, we won't have 2 again because this square will also times 2 here. So 4 cancel 4. So what we have here is y squared, then we have the y all over x, y the x squared. So we then write that y squared divide the x squared plus 2xy divide the x minus y squared is equal 0. What I'm doing here is, this is y squared, so equal this. So what I do is just to carry y squared to this side, and then we equate everything to 0. Now we are able to form a differential equation of first order, because we have only one constant and we expect differential equation of first order, but it has degree 2. Yes, so that is how we can form a differential equation. Let's look at the next subtopic. Okay, another subtopic is solution of first order differential equation. Now, any first order differential equation will be solved based on the nature of the differential equation, like the given differential equation, using any of the underlisted methods. One, we can solve first order differential equation by direct integration. Number two, we can solve first order differential equation by separation of variable method. Now this one is direct integration method. Now we have another one, We can solve it by substitution. By substituting y is equal vx if the first order differential equation is homogeneous. So these are the methods we are going to look at. Now let's look at direct integration method. This method could be used if the differential equation is of this form. Solve the differential equation s squared plus 1 divided by x is equal to x. Now let's pick the solution. You see that x squared plus y divided by x is equal to x. Could be written as dy dx is equal to x over x squared plus 1. And as it is, we can integrate it directly. So integrating both sides with respect to x, we'll have integral y dx. The x is equal integral 2x x squared plus 1 dx. Then we know that this can cancel this, so we have integral dy will be equal integral 2x x squared dx. So this side become y is equal integral 2x x squared plus 1 dx. Now we recognize this function from our elementary calculus when we talk about integral calculus, that if we have a function such that the derivative of the denominator is on the numerator, then we can have it to be ln of the denominator. But let's just recall how we perform the integration. Let z is equal x squared plus 1. You see that the z all over the x will be equal to x, which implies that the z will be equal to x dx. So now we have that y is equal integral dz all over z, because z is x squared plus 1. Okay. In that way, we know that this is the same as integral 1 all over z dz, which we know as ln z. Yes, we know as ln z plus c. Okay, but z is equal x squared plus 1. So we have that y is equal ln x squared plus 1 plus c. So that becomes the function. This is the function that if we differentiate this function, we come to where we have this differential equation. So now that we are solving the differential equation, we get back the function. In solution to differential equation, we start from the differential equation to go back to the function. While in formation, we start from the function, coming back, going to the differential equation. So that's how simple it is. That's how simple, by direct method. Another subtopic we are going to look at is solution by separation of variable. If a first order differential equation is of the form x is equal f of x times g of y the equation cannot be solved by the direct integration method, since the function g of y prevents the differential equation to be solved by direct integration method. Hence, we apply separation of variable by separating the function g of y to the left hand side, and f of x will be in the right hand side. So if we do that, we can separate here to come to this side, and then f of x will be here, and then the x will also come this way. So in that way, we can now solve it by direct integration. So that's what we say. Hence, we apply separation of variable by separating the functions g of y to the left, and f of x will be in the right hand side. Thereafter, we solve by direct integration method. So thereafter we can solve by direct integration method. So we'll look at example of functions that we cannot solve by direct integration but solved by separation of variable. So the example will be of this form. For example, solve the equation sin x all over 1 plus y divided by x is equal cos x. Now, we see that this equation, because of the way it is, that sin x here, sin is a function of x, which we know. So, and this is y. I mean that sin x, we can separate this to be this way, so that we'll have y function this way and have x. Then we can now integrate it. You know, this function as it is a function that you cannot integrate directly. That's why we said that if a first order differential equation is of the form y to x equal f of x times g of y. So here, g of y prevents the equation to be solved by direct integration. So we use separation of variable techniques. Now, let's take the solution. Sin x divided by x all over 1 plus y is equal cos x. Now, if you look at this equation, you see that this equation, we can write it in this form: 1 all over 1 plus sin y, 1 all over 1 plus y all over sin x divided by x is equal cos x. You know that this is the same with this because automatically what it means here is that we have 1 plus y all over sine. So what it means is that this can be multiplied by this. That is how we get this. So 1 was divided by 1 plus y all over sine. And so here we can now write that dy dx, okay, that 1 all over 1 plus y divided by x will be equal cos x all over sin x. So as it is, we are now able to get the y function this way and the x function this way. So by integration, integrating both sides with respect to x, we have integral 1 plus y dy, because this will cancel this, will be equal integral cos x all over sin x dx. And as it is, we see that this can give us ln of 1 plus y will be equal ln of sin x plus c. How? Because this is the derivative, you know, cos is the derivative of sine. So now you see that in both sides we have ln, so we have 1 plus y. If we can write it ln 1 plus y is equal ln sine x, of course, we have ln c. So that this side can write it as ln of sine x times c. That's what it means according to logarithm, the law of logarithm. Which, if I can write this as any constant a, if a can represent this, so I will have it in this form, which means ln 1 plus y is equal to this. So by the time they cancel ln, we have 1 plus y is equal sine, or let's call it a sine x, so that y is a sine x minus 1. So we now get the function. This is how we can do it. But we'll take one example to also see it in another way. So next example, solve the equation dy dx is equal to exponential x minus 3y. Now, the solution will be in this way. Dy dx is equal to exponential x minus 3y. You see, as it is, we cannot integrate it directly because of this. And so, we can write it as dy dx is equal to exponential x all over exponential 3y. That's what it means. You know, according to law of indices, if I have something like this divided by this, I can take it up. And so, what it means is that even as it is, you cannot integrate it. But we can write this as 1 all over exponential 3y dy dx is equal to exponential x. And by this way, we see that we can integrate it, not even one, okay, because with this we can keep it here. By dividing, we go to this way, so we have it this way, which means integrating both sides with respect to x, we'll have integral exponential 3y dy will be equal integral 2 exponential x dx. And if we integrate this, we then have 1 all over 3 exponential 3y will be equal to exponential x plus c. That exponential 3y will be equal 3 to exponential x plus c. You know we are cross multiplying. Now, if I take ln of both sides, I will have 3y is equal ln 3 to x exponential x plus c, which means y will be equal ln 2 exponential x plus c, because over 3, because these 3, of course, these 3 can cancel these 3, so we'll have it in this way, to have it in this way. So that's how it will be solved. Another method of solution is solution of first order homogeneous differential equation by substituting y is equal v times x. First, let's talk about first order homogeneous equation. And for a differential equation, in which the powers of the variable in every term are equal is called an homogeneous equation. To solve this type of equation, we make the substitution y is equal to vx. So a differential equation in which the powers of the variables in every term are equal is called an homogeneous differential equation. To solve this type of equation, we make the substitution y is equal vx. So let's look at example of homogeneous equation and how we can make this substitution to have the solution. So we look at this example. Solve the equation xy plus y squared dx minus x squared dy is equal 0. Now this is homogeneous equation because the powers of the variable at each term is are equal. Look at it. This power 1, so we have power 2 in this term. This term we have one variable here and it has power 2. This term we have one variable here, it has power 2. So all the terms, in each of the terms, the powers are equal. And so we can take the solution in this form. We have xy plus y squared dx minus x squared dy equals 0. We can write this as x squared dy is equal xy plus y squared. What I just do is to carry this one this way so that the minus will go. Now, dividing both sides, by the x, of course, this is the x. So if I divide both sides by the x, I have x squared dy dx will be equal xy plus y squared. Now, dy dx will be equal xy plus y squared all over x squared. Alright, so, and this, we see that it's difficult to solve it even by separation of variable. It will be very difficult. And so the only way you can solve it is by making a substitution. Now, let y is equal vx. This is the substitution we'll make. So that dy dx will be equal, dy dx will be equal v. This is product rule. If you keep v, it differentiates x it will be 1 plus if x differentiate v, which is the v, the x, that is dy dx. So that from this equation we can then have that dy dx is now represented by this, where we have v plus x dv dx equal, y is equal vx. So we have vx squared, because if we put vx here, we have vx squared. Or let me give it directly so that you see it clearly. Vx in the place of y plus vx squared, because this one carries square, all over x squared, which will further give us that v plus x dv dx will be equal, we have vx squared plus v squared x squared all over x squared. Right. So we'll now have from here that this one's there's something common. There's something common there, so we can do it this way. V plus x dv dx will be equal x squared v plus v squared all over x squared. Now this can cancel this, so that we have v plus v squared, because this cancels this, so we have v plus v squared. And then we further have that v plus x dv dx is equal to this, which means x dv dx will be equal v plus v squared minus, I'm taking this one across, minus v, so that we have that x dv dx will be equal v squared. And as it is now, I have this function dv dx. This is v. So by separation of variables that we have said that we can solve it by separation of variables after putting the substitution. So by separation of variables, we can write it in this way: 1 all over v squared, the v, yes, the v, okay, the x, I put it that way, will be equal 1 all over x. Now integrating both sides with respect to x. Integrating both sides, we have integral 1 v squared dv is equal integral 1 all over x dx. So you can see that we have succeeded in bringing v one side and then x one side. So by integration, we will have that ln v squared is equal ln x plus c, which we can further write as ln v squared is equal ln x plus ln c, which is the same as ln ax, that is a represents ln c. So we have ln v squared, ln cancel ln, and then we have v squared is equal ax. Now recall that y is equal vx, so that v only will be y all over x. Now we can put this here, okay? We can put this y all over x. In this place we will have y all over x squared is equal ax. So we have y squared all over x squared is equal ax. Now, y squared by cross multiplication will be ax times x squared, which is equal ax cubed. So that is y squared is equal to ax cubed. So that y only is square root of ax cubed. So this is how we can solve to get the function. Is very easy to deal with substitution method. So we also take another example. Solve the equation x squared plus 3y squared dx minus 2xy dy is equal to 0. And we also observe that every term in this equation has power 2. So that is how we can recognize first order linear homogeneous equation. That is how we know whether the equation is homogeneous. When you look at the term, in each term you see that the powers are equal. Now the solution is in this form: x squared plus 3y squared dx minus 2xy dy is equal to 0, to be written as x squared plus 3y squared dx will be equal to xy dy. So that dividing both sides by dy or by the x, by the x, we have that 2xy dy dx will be equal x squared plus 3y squared. The x will cancel here. So we now have that dy dx will be equal x squared plus 3y squared all over 2xy. So we have it that this is homogeneous. We cannot. Now let y is equal v times x. We then have that dy dx will be equal v times, you differentiate x, which is 1, plus x times dv dx. That is by product rule. So that we have this, we can now substitute it here to have, in the place of the y dx, we have v plus x dv dx will be equal x squared plus 3y squared, and y squared will give us vx squared all over 2x, then y is vx. So that we then have x squared plus 3v squared x squared all over 2x squared v, which is the same as, we can factor out this to have x squared, then we have 1 plus 3v squared all over, the downside will be written as x squared, then we have 2v. So that this can cancel this. If this cancels this, we then have that v plus x dv dx will be equal 1 plus 3v squared all over 2v. Now, we'll collect like terms by transferring v to here. Then we have x, the v, the x will be equal 1 plus 3v squared all over 2v minus v. So we can take LCM of this side. You know that the LCM will be 1 plus 3v squared, LCM is 2v. Then this is over 1. So when we times it, we have minus 2v squared all over 2v, which will give us 1 plus v squared, 3v squared minus 2v squared, because v squared, all over 2v. So that means x, the v, the x is equal to that. Or we can write it clearly that x, the v, the x is equal 1 plus v squared all over 2v. Now here, we come to a stage where we can apply separation of variable. By separation of variable, we see that we will have that 2v all over 1 plus v squared. Yes, the v, the x will be equal 1 all over x. Now, integrating both sides with respect to x, I'll have integral 2v all over 1 plus v squared. The v will be equal integral 1 all over x dx. So, we know that this is the derivative of the denominator. So, as we know, we have ln 1 plus v squared will be equal ln x plus c. Now we have ln. So we can write it as ln 1 plus v squared, which is equal ln x plus ln c. Is the same as ln ax. I represent this by a constant a, and then by law of logarithm, we know when we have plus, we can multiply to have this. So ln 1 plus v squared is equal this. So this can cancel this ln on both sides. We have 1 plus v squared is equal ax, which is the same as writing that v squared is equal ax minus 1. But y is equal vx, which implies that v will be equal y all over x. That's what it means. So we'll now substitute that here because we don't need v. What we are solving for is y. So we now have y all over x, that is in place of v squared, is equal ax minus 1, which will further have that y squared all over, if you multiply it, x squared is the same as ax minus 1. By cross multiplication, we have y squared is equal x squared ax minus 1. So y only will be the square root of x squared ax minus 1. So that becomes the function. You can now solve it to get the function. So it's very simple it's very simple to solve it by method of substitution. Now we'll take some exercises. At this exercise, form a differential equation from the function y is equal exponential x times a cos x plus b sin x. Number 2, solve the following equations. Y dx is equal x squared plus y squared. all over xy. 2 is divide the x is equal to x squared plus xy plus y squared all over x squared. Then 3 we have 2xy plus y squared dx minus x squared plus xy dy is equal to 0. So these are the sizes that we are going to try by yourself from what we have learned, so you can do it very easily.